Hello friends, this is Priyanka. Today we are going to understand some basic concepts for the hydraulic machines or turbines. In this video we are going to understand how to draw the velocity diagram for different conditions for the inward radial flow reaction turbine. So let us first understand what is this inward radial flow reaction turbine with the help of diagram. Now if we observe the diagram, the water from the casing enters into the guide wheels in which there are the stationary vanes are there. And what is the work for these stationary vanes? These vanes directs the water from the casing towards the runner, and in runner there are moving vanes. So why this turbine is called as inward radial flow turbine? Now in runners there are moving vanes and water from the outer periphery is moving towards the inner periphery of the runner. That's why this is called as inward radial flow turbine. Now we will consider one blade from the runner. So if we observe this diagram, here is the runner in which there is one of the vane is getting selected, for which this point A, that is on the outer periphery, is the inlet tip. And what is the diameter for this outer periphery of the runner? That is D1. And we will consider the another point, that is point B, which is on the inside periphery. We will say that this is the outlet tip, because water is entering from this outer periphery to the inner periphery. That is, the direction is from outward to inward direction. And what is the diameter? So diameter is D2. And that's why this is called as inward radial flow turbine. Now we will draw inlet velocity diagram. So for that, at the inlet tip A, we will draw one tangent, because this point A is on the circle. So at this point A, we will draw here one tangent. Now all the velocities at the inlet tip, we will use here the suffix 1. So we will consider here u1, that is the peripheral velocity at inlet point A is along the tangent to the wheel at A. So when we show this u1, that velocity u1 is along the tangent to this point A. So we have to show here velocity u1, that is along the tangent to this point A. Now how to calculate this u1? So this u1 is equal to pi d1n by 60. Now why diameter d1 is taken? Because here the point A is on the outer periphery of this runner, and here diameter is d1. So I will write here this is the runner. Now alpha. So we will consider here the alpha, that is guide blade angle. So we know that water first enters into the guide wheel, and in that wheel there are the guide blades which are stationary, and this guide blade angle is known as alpha, and that is also, we can say, angle made by absolute velocity v1 at the inlet. So how to draw this v1? So we will first draw here one line. So I will draw here the v1, that is velocity v1 with angle alpha. So for that I will draw here, this is the velocity v1 and angle alpha, that is the angle, that is the guide blade angle. So I will say here is the angle alpha, and this is the velocity v1, that is the absolute velocity at the inlet tip. So I will show here this is the velocity v1. Now here theta. So theta is the angle made by relative velocity vr1 at the inlet. Now we are going to understand what is the velocity diagram at different conditions, and for that different condition that is getting affected by this angle theta. So what is the first condition? So first condition is that when this angle theta is acute angle, And what is this angle theta? That is the angle made by relative velocity at the inlet. So we have to draw here relative velocity at the inlet tip A, but with angle theta is the acute angle. So I will draw here one relative velocity. But before that, what is the point for that? So for that is we have to take here one point to join this inlet tip. So how to decide this point? So for that we have to take, or we have to draw here this u1, that is the peripheral velocity at the inlet point A. So now if we observe, this is the tangential line to the point A and this line is parallel to this tangential line. So we can show here the velocity u1 along this line. And when this theta is acute angle, what is the condition? That is the world velocity at point 1. That is VW1 is greater than U1. So this is related to angle theta. So we have to show VW1 is greater than U1. So first I will show here the VW1. So how to show VW1? So for that we have to draw here velocity of flow. So velocity of flow, I will draw here one straight vertical line. And we have to show the direction, that is VF1. Now this total length is known as VW1. So I will show here VW1. Now theta is the acute angle, that is the angle made by relative velocity. So we have to again draw here u1. So u1 is less than vw1. So I will show here at some point there is u1. And here is the point. So now if I join this point to the inlet tip, that will be the velocity, and we have to take care that theta is the acute angle. So we have to draw here one theta line. This is the angle theta, that is the acute angle, and here is VR1, that is the relative velocity at the inlet tip 1. So if we observe for this case first, when theta is the acute angle, VW1 is greater than U1, then here is the angle theta, here is the V1, here is the angle alpha. Now from this diagram we can write that what is the value of tan alpha. So tan alpha is equal to, so what is the opposite side? VF1. And what is the nearby side? That is VW1. Now in the same way we can also write what is the value of tan theta. So tan theta is equal to, this is the VF1 divided by, now how we can decide this length? That is VW1 minus U1. So this is the velocity diagram for the first case. Now we will move for the second case when theta is equal to 90 degree. So when theta is equal to 90 degree, that means this is also called as radial vanes, that is inlet vane angle theta is equal to 90 degree, that means radial vanes are there. So whenever in the question it is mentioned that the radial vanes, then we have to take theta is equal to 90 degree. Then what will be the velocity diagram? So first I will draw here the absolute velocity V1 with an angle alpha. So I will draw here at the inlet tip A, here is the absolute velocity and angle alpha we have to show here, that is we have to take this line parallel to the tangent at this point, and here is the angle alpha and here is the absolute velocity V1. Now here theta is 90 degrees. So what is, how we can define theta? That is the angle made by relative velocity at inlet. So when here I will show relative velocity at inlet, but now for this relative velocity at inlet we have to show vertical line, straight vertical line, because this line is horizontal, this tangent is also horizontal. So I will show here this theta is equal to 90 degree and here this is VR1. So what is happening when theta is equal to 90 degree? In this case, VW1 is equal to U1. So here I will show this total distance, that is VW1 is equal to U1, and this VR1 which is equal to VF1. So how we can define this tan alpha? So tan alpha is equal to, so we can take here VR1 or VF1. Here I will write or VF1 because both are the same, divided by VW1 or U1. So this is the value of tan alpha, and this is the structure of the inlet velocity diagram. Now we will move for the case 3 when theta is obtuse angle. So how to draw the velocity diagram? So first I will draw absolute velocity with guide blade angle alpha. So here this is V1 with guide blade angle. So for this angle we have to take line parallel to this tangent, and here is the angle alpha, and here is V1. Now theta, how to draw this theta? So if we observe, it is given that the angle made by relative velocity at the inlet tip. So I will draw here this is the angle, or we can say here this is the relative velocity, that is VR1, and this is the angle made by relative velocity at the inlet. So I will draw here, this is the angle theta. Now we have to show VF1. So how to show, that is the flow velocity. So what is happening in this case? So in this case U1 is greater than VW1. So this starting point to the end point I have to show U1 because here U1 is greater. Now how to define VW1? So VW1 is less than this U1. So if I select this point, or I will take here VF1, that is the flow velocity. So for that I have to take here one vertical line, and this is called as VF1. So here is the point. So from this starting point to this point, here is VW1. So this is the velocity diagram. Now how I can define here this angle theta and alpha? So this remaining angle is 180 minus theta. So for this 180 minus theta we will write the equation. So how to write? So tan of 180 minus theta is equal to, so opposite side is VF1 and nearby side, that is U1 minus VW1. Now how we can write the tan alpha? So for this tan of alpha, it is simple, that is opposite side is VF1 and nearby side is VW1. So this is the velocity diagram when this theta is obtuse angle. Now we will move for the outlet velocity diagram. So for that we will use the angles beta and phi instead of theta as well as alpha. Now what is the condition? So we will consider here the case 4 when velocity of whirl at outlet is in the same direction at inlet. So what is happening? So for this condition U2 is greater than VW2. So what is U2? So we know that U2 is the peripheral velocity at outlet point B along the tangent. So first I will draw one tangent line at the outlet point. So here is the point B, so I will show here, and at this point B, this is the tangent line in the form of dash I have shown. So we can show this velocity U2 along this tangent line. So first I will draw here one line parallel to this tangent line. And now in this case u2 is greater than vw2. So first we have to take here u2. So how to show that? So for that we have to take here one relative velocity. So how to plot the relative velocity? So relative velocity is, we can plot with the help of angle phi, and this angle phi is the runner vane angle at outlet. So here we have to draw one runner vane angle at the outlet. So this is the tangent, and for this tangent, so here is the line parallel to tangent, and here if I draw here one line, then this angle phi is the runner vane angle at outlet. That is, this is the angle between VR2 and tangent. So here I will show VR2. Then I have to show here U2 is greater than VW2. So how to show? So first I will show here one whole, for this whole length I will say this is U2. And now I will take here the angle beta. So how to take the angle beta? So angle beta is the angle made by absolute velocity at tangent to outlet B. So this is the tangent line. So at this tangent, angle beta is angle made by absolute velocity. So with the help of angle beta, I will draw here one absolute velocity line. So this is the angle beta, and here absolute velocity I will say V2. Now I have to plot velocity of flow Vf2. So we know that it is, we have to draw one vertical line from this outlet tip. So here is Vf2 and this is the direction. So from this point to this end point, we can say that is the value for Vw2. So this is the velocity diagram. Now from this diagram, how we can define the tan phi? So tan phi is equal to, so if we consider this triangle Vf2 divided by, now what is the length of this line? That is U2 minus Vw2. So when velocity of whirl at outlet is in the same direction of inlet, then we have to use this formula, and this is the velocity diagram. Now we will move to the next case, that is when velocity of whirl at outlet is in the opposite direction of inlet. So in this case, VR2 cos phi is greater than U2. So first we will plot the relative velocity at outlet. So we know that how to plot, that is relative velocity at outlet we have to plot with the help of the angle phi, and angle phi is the runner vane angle at outlet. So with tangent, so first I will draw here one line parallel to the tangent, and then with this angle phi I will draw here relative velocity at the outlet. That is, here is the angle phi, here is VR2. Now VR2 cos phi means what? So here this is the line, that is VR2 cos phi. This line indicates this VR2 cos phi, and that is greater than U2. So we have to show U2. So before that we will show what is the velocity of flow, that is Vf2. So we have to draw from this outlet point one vertical line, that will be Vf2, and then we have to show V2. So how to show V2? So for that, with the help of angle beta, we have to show absolute velocity. So this absolute velocity, that is, what is the angle beta? That is the angle made by absolute velocity at tangent to the outlet B. So this is the line along the tangent. So if I show here V1 with this angle beta, so here is the angle beta and this is the absolute velocity V1, then from the starting point up to this point, here is value of U2. And this whole length is known as VR2 cos phi. So here remaining value we have to show, this is the value for VW2. that is the whirl velocity at outlet. Now from this triangle, so how we can find out the tan of phi? So tan phi is equal to, so here we will refer this whole triangle, so which is equal to Vf2 divided by u2 plus Vw2. So this is the velocity diagram for this case phi. Now we will move for the next case 6. So what is this condition? That is when velocity of whirl at outlet is 0. So how to show that? So we can say that Vw2 is equal to 0, and this condition is also known as the radial discharge. So first we will plot here what is the VR2. So VR2 we have to show with the help of angle phi, and first we have to show here the tangent line, that is we have to draw one line parallel to this tangent. So I will draw here one line parallel to this tangent line, and along this line we can show the velocity u2, that is the peripheral velocity at outlet along the tangent. So here along this line there is u2. Now how to show vr2, that is relative velocity? So for that we have to take angle phi, that is the runner vane angle at outlet. So with this angle I will show here. So for this tangent line here is the angle phi, and for this line there is VR2. Now here Vw2 is 0, that means here only u2 is there, and when this Vw2 is 0, then what is the angle beta? So angle beta, that is the angle made by absolute velocity at tangent, that is 90 degree. So we can say that for this condition beta is equal to 90 degree. So I will show here one line, vertical line, and here is the beta, and that is equal to 90 degree. So this vertical line indicates Vf2, which is equal to V2. That means V2 absolute velocity and flow velocity are equal, angle beta is 90, and here this line indicates only u2 because Vw2 is equal to 0. So if we observe this diagram, how we can define the tan phi? So tan phi is equal to Vf2 divided by u2.